Hello all and welcome to another week in Intro to Calculus. We are going to talk about using integrals to find volume, and there's lots of different figures that we can use integrals to find volume for, and we're going to focus just this year on revolved figures. So those are things that look like this, where we take an area and we rotate it around so that it forms usually a vase shape, something cylindrical or circular, something like that. If you're interested in seeing other different types of volumes, they will be addressed in future calculus classes that you take. But for now, let's get ourselves ready for notes, and we're going to get started talking about revolved figures. So the idea here is find the volume created when we rotate a region around, in this case, we're going to focus on one of our two axes. So either rotating around the x-axis, where in this case this would form a lovely sort of vase shape, like so. Or you will also have ones rotate around the y-axis, but generally those will be in terms of y as a function, and then around the x-axis will be in terms of dx like this. So if it asks around the y-axis, just change it to a function of y. You can use the same formula. Now, the way we arrive at this formula for the volume is that as we revolve the shape around the axis, we create what are sometimes called discs, or they're just little cylinders. So it's like almost like a coin shape, where this is our outside and it is the dx, it's the change in x, and then it's got a radius here as it creates the disc, which is the same as this length here, which is determined by the height of the function f of x. So we're going to use basically our cylinder formula, because that's what this disc is, this coin shape, is pi r squared times h. The r is the height here of the function, and the width of the disc is dx right here. So the volume of this entire figure is the integral from a to b, so a and b, pi times f of x squared dx. And that's the formula you're going to want to use for this lesson. Now, number one, find the volume created when the region R enclosed by the function y equals root x minus 1, x equals 2, x equals 5, and y equals 0 is rotated around the x-axis. Now, the important thing here is y equals 0, this just is the x-axis. If it was x equals 0, that's the y-axis. So it's sounding a little fancy, it's just the axis itself. So the first thing I'm going to do is I'm going to sketch what this curve looks like. So y equals root x minus 1 is going to be square root formula like that, the positive. From x equals 2 is the vertical line here, to x equals 5, like so. And so we can see that the area that we're going to revolve is this here, not the neatest drawing. And what that tells us, looking at our formula and function here, is that this is our a, here is our b, f of x is equal to root x minus 1, like so. So that gives us our bounds, and we can plug it into our formula. So the volume of this figure, as we rotate it around, it's going to create sort of like a bowl shape, would be the integral from a, which is 2, to b, which is 5, of pi times f of x squared, so root x minus 1 squared dx. Just plugging it into the formula right here, and now we want to simplify and evaluate. I'm going to take the pi out as a constant coefficient, and so then the integral from 2 to 5. The root and the square also cancel out, so it's the integral of x minus 1 dx from 2 to 5. Now, that is a definite integral, so I'm going to go first find the antiderivative, which would be x squared over 2 minus x from 2 to 5. So that's pi times the difference with 25, 5 squared over 2, minus 5, minus 4, 2 squared over 2, minus 2. Then when I evaluate that, 25 over 2 is 12.5, minus 5 is 7.5, 4 over 2, so pi 7.5, minus 4 over 2 is 2, minus 2 is 0, so the final volume is 7.5 pi of that bowl figure. Now, as I said, here we can see we have a problem with the y-axis. Write the integral, so we're not evaluating it here, to find the volume created when the region bounded by x equals y minus y squared and x equals 0 is rotated around the y-axis. So remember, the x equals 0 is the y-axis the same way x equals 0 is the x-axis. Sorry, y equals 0 is the x-axis. So it's still, I often find helpful for me to illustrate. Now, this function is a little bit challenging because we're not used to seeing it in terms of the variables shifted. We're used to y is equal to x minus x squared. Well, it's going to be the same basic idea, except for instead of being on the positive x-axis, we're going to go on the positive y-axis, and our two roots of this function, if I said 0 is equal to y minus y squared, we'd solve it the same way through factoring. And we see that our roots are at 0 and 1, and it's going to be a parabola in the first quadrant, like so. So what this tells us here is that this is the region that is bounded by the parabola and the axis, and we have our bounds 1 and 0 from the quadratic factored here. So those are our bounds, and since we're going around the y-axis and our function is in terms of y, we can just use this same formula but with the variable changed. So f of y squared dy. All it is changing the variable. We're used to seeing our variables change in terms of x. We could have t, we could have theta. Same here, we could have y, as long as everything is switched. So here our bounds are 0 and 1. Pi, the function is y minus y squared. We square that as well from the formula here, dy. And that would be the value of our integral. And just ask you to write it so you don't have to worry about evaluating it at this point. If you have questions about using this formula for rotating around the x or y axis, please let me know. I have changed office hours from where we were during the majority of this year because of when my middle school classes are, but I'll still be available during office hours on Zoom using the appointment calendar or by email or in the comments.